Hello, I am a PhD student at the University of Waterloo, advised by Professors Kimon Fontelakis and Okosh Jagannath, who are also my co authors. And I'm very excited to present our work on the effects of graph convolutions in multilayer networks. So, here's a brief overview of our main contributions. We completely characterize the capabilities of up to two graph convolutions in neural networks with up to three layers for node classification tasks. First, we show when and by exactly how much do convolutions improve the performance of learning models. And second, we show how the placement of convolutions across the different layers of a network affects their performance. For theoretical results, we study a statistical model called the CSBM, which I'm going to describe soon, and for empirical demonstrations, we use synthetic data plus several known benchmark datasets. So we look at one of the most popular types of GNNs, the graph convolutional network or GCN. To briefly describe what a GCN is, let's say we have a data set of n nodes where each node has some features denoted by x, and there's an undirected, unweighted graph that models relationships between the nodes with adjacency matrix denoted by A. Then a graph convolution updates the representation of node I to be basically the average of the features of its neighbors. Our goal in this paper is to analyze what happens when convolutions are placed in various layers of a multilayer network and how the performance of a network changes with the number of convolutions. So, to do that, first let's define the architecture that we're going to study. We make a very simple modification to the well known GCN by Kiff and Welling, where we have a variable number of convolutions in each layer L denoted by K sub L. Note that if K sub L's are all ones, then this is the standard GCN. We also note that such architectures have been empirically shown to have state of the art performance on node classification tasks. In particular, our theory aligns with the empirical results of APPNP, where all power iterations are placed in the last layer. So let us now describe the statistical model on which we base our theoretical results. To motivate the choice of this model, we observed that linear classifiers are easily realizable by one layer neural networks, and the class of one layer neural networks is too simple to capture the extent of the effects that we aim to study. So we need to look at multilayer networks. For placement questions in particular, we necessarily need to look at multilayer networks. At the same time, we still need the data model to have an intuitive signal to noise ratio that helps us characterize the theoretical results. So, we propose to study the contextual stochastic block model, or CSBM, modeled after XOR data. So, there are two classes of nodes, C0 and C1, and each node has a feature vector. These features are drawn from a four component Gaussian mixture with means mu, minus mu, nu, and minus nu, and the same variance sigma squared. So class C0 contains a uniform mixture of nodes from the Gaussians with means plus minus mu, and class C1 contains nodes from the Gaussians with means plus minus nu. All node features are assumed to be mutually independent, and in addition, there is an independent graph structure that is modeled as a stochastic block model, where the probability of an edge between nodes I and j is p if they are in the same class and q if in different classes. We also identify two relevant signals in the data. So zeta here is the ratio of the distance between the means to the standard deviation of the mixture, and gamma is the relevant signal in the graph. And here's what the data looks like for two dimensions. So the XOR arrangement compels that multilayer networks are used since the means of the data are not linearly separable. Moreover, this serves as an example where putting a convolution in the first layer hurts classification accuracy. If interested, please check out the paper for more details on this. But let's move on to the main theoretical result where we want to understand the effects of convolutions on the CSBM data model. First, we establish a baseline for neural networks that do not consider the graph structure at all. We show that universally, any classifier that does not use the graph makes a mistake on at least f fraction of the nodes where f is given in the display. Phi sub c here is the complementary CDF of a standard Gaussian. So the intuition from this expression for f is that first, if the signal zeta in the mixture is very large, then there exists a classifier that makes zero mistakes. Second, if the signal is very small, then any classifier will make a mistake on half of the nodes, meaning that no one can do better than a coin toss in this case. And third, if the signal scales with at most square root log n, where n is the number of nodes, then an ideal classifier will still make a constant number of mistakes. From this intuition, we conclude that to perfectly classify the data without using the graph structure, the signal needs to scale faster than square root log n. So now our main result compares the performance of neural networks with one and two convolutions with classifiers that do not use the graph. So we provide the fundamental thresholds here for networks with one and two graph convolutions to be able to perfectly classify the data. As we saw before, when no convolutions are used, the signal in the mixture needs to scale faster than square root log n. For a neural network with one convolution, the product of the signals in the graph and the mixture, that is gamma times zeta, needs to scale faster than square root of log n over the average degree. Note that n times p plus q is just 2 times the average degree. So the conclusion here is that if the graph signal gamma is good enough, say for example gamma is larger than 1 over the square root of expected degree, then a network with one convolution can perfectly classify the data in a wider regime compared to a simple MLP with no graph convolutions. Similarly, for a network with two convolutions, the product gamma squared times zeta needs to scale faster than square root log n over n, and this expands the regime of perfect classification even further than for networks with one convolution. Note that these conditions on gamma hold easily in most settings. For example, if p and q have the same scale in n, then this is true by a large margin. Now let's move on to empirical demonstrations. So here's a plot for synthetic data. On the x-axis is the signal in the mixture, and y-axis is the classification accuracy. In plot A, we see that for two-layer networks, two convolutions can classify the data in a larger regime compared to one convolution. And in plot B, we show the same thing for three-layer networks. Note that all networks with two convolutions placed in any of the layers perform mutually similarly and are better than all networks with a single convolution. Next, we show our results on some real world data sets. So here's the plot for OGB archive for two-layer networks. On the x-axis, we have the model name. So for example, the rightmost model is called 2L21, meaning that it's a two-layer network with two convolutions in the first layer and one convolution in the second layer. We report the performance of the models with all variations of the placement of convolutions. And it is interesting to see that all the models with the same number of convolutions, which are annotated by the same color here, perform similarly. Also, two convolutions are always better than one convolutions, as predicted by our theory, while three convolutions don't do much over two convolutions. Next, we have the same plot for three-layer networks where we observe the exact same trends. Then we have the same plot for OGB products, which is another data set for two-layer networks, and then for three-layer networks. There are more plots for other data sets in our paper along with more details about the experiments, so please have a look if interested. Finally, we have a few concluding remarks. So our main contribution is the theoretical characterization of the capacity of graph convolutions and their placement among different layers of a neural network. We identify the relevant signals in the data and provide high probability guarantees about classification in terms of these signals. Also, we show that any combination of convolutions achieves similar performance if the number of convolutions is the same. So that marks the end of the presentation. Thank you.